Hello, everybody, and thank you for joining us. I'm Janice Landsfeld. I'm now an application specialist with SonTek. Some of you may remember me from my time helping you for the past 5 years troubleshoot technical issues as a tech support representative. And I'm joined today by Nauman, President and Senior Engineer at HydroScientific West, one of SonTek's authorized dealers here in the U.S.
Good morning, everybody. Good afternoon or good evening, wherever you happen to be on this planet.
That's right. What we plan to do in this webinar is give you an overview of the SonTek-IQ instrument with particular emphasis on the IQ pipe. And Ron will offer some insights from his extensive work in all kind of real-world field applications. Hopefully it will be a useful bit of theory and real-life application. What we're particularly excited to talk about, as I said, is the latest model in the series specifically designed for pipes. But first we'll overview the IQ series in general, how the IQ pipe fits in. We'll discuss the instrument features. We'll compare and contrast the different models. I'm sure there'll be some questions on that. And lastly, we'll present some data and installation examples. So hopefully, I hope you'll see we designed it with real concerns, your concerns in mind. And if you have any questions as we're going along, please feel free to type them into the chat box that should be somewhere on your screen. And at the end of the presentation, we'll try to address as many of those as possible. So first I'm going to talk a little bit about the IQ series. We went into greater detail in a previous webinar earlier this year when the IQ Standard and IQ Plus were released. So just a quick overview on what led to the development of the IQ. SonTek, with a grant from the United States Department of Agriculture, recognized that here in the U.S. and all over the world, water supplies and their management are increasingly complex, and all of us out there listening, I'm sure, are recognizing the need for more accurate, trustworthy data. So we took this big picture in mind and set out to develop an instrument. And not just an instrument. There were two parts to this development. Of course, we wanted to build a good instrument, but we also really wanted to understand, sort of set aside textbooks and assumptions for a second, and really understand flow in open channels and in pipes, and with this knowledge, give the instrument the best information to work with. We didn't know what it would look like. We didn't even know that we wanted to call it the IQ. We really set out to do our homework first. And as this graphic nicely illustrates, what this entailed was going out to sites, all shapes, all sizes, all flow conditions, and really just taking multiple measurements, in some cases 100 measurements at over 100 sites, and from a lot of single point measurements, truly map the flow field and see what it looks like, as you can see in this colorful graphic at the bottom. And as we found in some situations, not all flow is going to be textbook. You can see in this example where you might expect the highest velocities are not there. They're up here. And where most instruments do their measurement is in the center. So if you would do a theoretical calculation in this particular example with an instrument where it normally goes in the center of the channel, you would probably underestimate your flow.
I think another reason as well that was driving force or a catalyst for this was to begin to look at not so much as a replacement. Well, it could be a direct replacement of the SW. That architecture, firmware, the processor is getting on in years. That thing was developed in 2001, and so it was time to use current state-of-the-art technologies, and then as well as what was collected in the field and the empirical data that Greg and John put together, and come up with a more robust, more accurate, more pertinent especially to the irrigation market.
So after all the development was done, this is what we have. This is the first model that came out, the IQ Plus and the IQ Standard for small streams and open channel man-made or man-made channels. There's a lot of features that we packed the IQ with, but basically it is an instrument that measures water level. There's two ways of it doing that, acoustically and with a pressure sensor. We'll talk more about that later. It measures velocity, but it does so in both the horizontal and vertical direction. So it is velocity, but it's velocity in a way that's different than SonTek has ever done it before, and it's different from the way anyone else does it. And it measures temperature. And from those three fundamental measurements, we're able to do a calculation, which is what most people are interested in, of flow and total volume. That's basically how it works. So what is different now? What does SonTek do that it didn't do before, and what does it do that nobody else does? Well, I like this graphic. What you see on the left there is a pretty standard looking velocity profile. We're looking at a velocity profile from the side there. This would be our water surface. This would be the bottom. The instrument would be right here, sending an acoustic signal back, and this is what the data would look like. And if you can draw a curve through that. If you averaged it long enough, you'd get a decent curve and be able to glean enough information. But what we have now with the new technology, the new transducer technology, the new proprietary flow algorithms, just to name a few, is with less averaging, you really don't even have to draw a curve. The data itself is a curve. And not only that, but you have less guesswork to do with unmeasured surfaces. So there's less extrapolation to do at the bottom, because instead of a blanking distance of a certain distance for other instruments, we actually have data down here. So there's just less guesswork down here, and then there's less cutoff at the top. You can even start to see very detailed information, such as in this example, where there's even a subsurface maximum.
Yeah, the thing I'd just like to enhance on is that you can see the older SW or SL technology, only after a 60-second average, you still had a pretty wide precision or standard deviation there of your velocity data. So only 30-second average. You're a lot more cleaner. It's a lot tighter, obviously. A lot more precise and accurate. And the reason, one of the reasons why, is that this thing is sampling at a much higher frequency than the older systems, potentially up to somewhere between 60 and 70 hertz. What this affords you and buys you, though, is that you can start to use where the older Argonaut technology, at a point where you may want to use it for control, was pretty tough to do, especially if you wanted to make some quick control adjustments, say on a gate or something. With 30-second averages now, this thing now lends itself more to being used in a control application, as well as real-time monitoring.
Right. One thing I did want to hit on is this word SmartPulse. One thing I did want to mention is that SmartPulse is the name SonTek gives to its proprietary technology. We'll hit on that a little bit later too. But river surveyors, if you're familiar with that instrument, may already be familiar with this concept of SmartPulse, which is using 3 different processing techniques to come up with the best technique and the setup parameters on the fly based on the observed flow conditions in real time. So the instrument is not only collecting data and monitoring it, but it's looking at the depth, the velocity, and even the turbulence levels, and will switch its processing technique, and that's how we're able to get such clean data. So that's our summary of the IQ series in general, and now specifically on the pipes. Discuss a little bit about the development, and the development of the IQ pipe was similar to the IQ Standard and Plus, in that We really wanted to understand what pipe flow looked like, and what under different situations, and how to handle complexities. Like the IQ standard, we didn't assume that the beams were going to be at a certain angle. We didn't assume the form factor was going to assume a certain shape. It was a very empirical process to see what would give us the best information. We wanted it to work in pipe diameters ranging from about 1.5 feet up to 16 feet. We wanted to be able to make it work in all situations, whether the pipe was partially full, or pressurized to a certain extent. And of course, we want the flow data to be accurate. And I think probably just as important as all of the above, we wanted to make it easy to install and use over time or in the very beginning.
Yes. Yeah, very. Considering, you know, the Argonaut, the older SL, this thing probably in your installation time will be reduced by almost 50%. Smaller cables, less intrusive instrument to use.
And very compact. Yeah, one of the comments I often get when people see the IQ for the first time is, wow, I thought it was a lot bigger than that. But as you'll see in a minute, it's very compact. So here's just a picture to show you the test facility that was the NIST traceable facility here in the U.S. NIST is the National Institute of Standards and Technology, and this is at the Utah Water Research Lab. So again, we performed dozens of tests in a range of different pipe sizes, range of flow and depth conditions, and from this information we developed and refined our proprietary flow algorithms. And this is what it looks like. It is very compact. Like I said, we came up with the beam angles that we wanted. We changed the housing design to work better in pipes, and included our flow algorithms, which of course you can't really see in a picture.
No, but yeah, just to expand on the algorithms, there are the algorithms for open channel, of course. If it's a non-symmetrical, irregular, natural stream, the trapezoidal shape, typical canal, closed conduit, basically any type of symmetry that you encounter in some of the newer, some of the older installations or applications. This instrument will accommodate for it when you're entering the cross-sectional area.
Just to review some of the features in detail, as you can see here, we have, as some of our older instruments do, and the IQ Plus and Standard do, we have these centerline beams, one looking upstream, one looking downstream. But in addition to these, so this gives you your centerline velocity, but we also have these skew beams, one that looks out to the right of the pipe and one that looks out to the left, pointing forward. So as we say, we're getting a horizontal distribution of velocity, and we're getting this vertical distribution of velocity. Again, it's not velocity, it's a full velocity profile in cell sizes down to 2 centimeters. It also includes a temperature sensor here at the back, and pressure, there's a pressure port here on the side, and the acoustic beam, the vertical beam on top. And both the acoustic and the pressure sensor are used to give us water level measurement. It is a redundant measurement, which is nice to have, but it's not just that. SonTek has a way of using each one of these to monitor the other. So you could almost say that each one calibrates the other, and not only should you ever not have to be without level data, but it should always be accurate because each one is constantly monitoring the other.
More like a checks and balance on each, and offering some redundancy to the other, as well as if there are say an anomaly or one is not behaving correctly, you will get discrete error codes that you can look at later on that will tell you. But for the most part, again, checks, they are one is a backup of the other, and they are constantly switching based on the application, meaning not the application, but the situation, whether you're very low level water conditions or high water conditions, low velocity or high velocity.
And there's some mechanical things here. At the back, we have a power and communications connector, and then the housing itself shows you where the mounting bracket would go. It's kind of molded in here, and then we also supply the mounting brackets.
And then in addition, there's also a new, for using the IQ pipe, there is a new ring that was developed here at SonTek that comes in 3 flavors, meaning different diameters. I think a 24, 36, and 40.
Up to 48.
Oh, 48, okay.
Yeah, we'll show a picture here in a second.
So that mounting bracket will then attach to that ring, and it's an expandable ring.
And that's the instrument itself. This is all you need to get a velocity, flow, total volume measurement, but it does come with some accessories. And to note, people who might be familiar with the other IQs, all of the accessories are fully interchangeable among the IQ models. So this power and communications adapter can work on any IQ model. It essentially takes a signal from the IQ on this side. We have power and SDI-12 on this side, and then a serial out or Modbus out on this side. So the cable adapter is the same. If you do need an analog 4 to 20 milliamp signal, that is possible if you want the optional flow display too. Now, the flow display comes in 2 models. There's without analog output, and then there's with analog output. And again, the software is the same regardless of which IQ model you use.
Right. With the 4 to 20 milliamp outputs, there are, I believe, 23 different scalable parameters that you could map over to one of the outputs. So typically would be level, flow, volume, maybe signal to noise ratio as a determining the health or housekeeping parameter to look at for the station.
Right.
But again, there are 23, so a lot more options than what we had with just the 2 and the prior Argonaut platforms.
That's right. So just a nice overview of what exactly you get when you buy an IQ system. You get the instrument itself. You get the mounting hardware. So here's a picture of the mounting brackets, which you may or may not use depending on your situation. The power communications connector, the cable, which is different from the Argonaut cable. Maybe Ron can comment on the improvements we made on that cable.
Well, one great thing that they did with this is made it smaller. Typically, with the larger connector, the wet mateable connector on the prior series, you were looking at 1.5 inch, 1.25 inch conduit if you wanted to provide some mechanical protection for the device when you're installing it. This instrument, this cable now in the instrument is much narrower. So maximum size of conduit that you're dealing with, if you want to provide mechanical protection, is only 1 inch. You'll probably even get away with 3/4 inch if you just pulled in one direction. Also, one thing that is you need to pay attention with this instrument. not unlike the others, is that the connector on this is not wet mateable like it used to be. It's much smaller, so therefore when you make that connection, it needs to be dry. What else could we?
Also regarding the conduit, we just give you the flying leads at the end, and then the wiring harness to connect it to. So if you need to chop this off and make it shorter, or chop it off and pull it through, you can do that, unlike our previous cables.
Yeah, no more enclosures that have 10 or 15 feet of cable wound up inside of it because you were afraid to cut it or make it shorter for the application.
Right. That's the function of this power communications piece right here, so you can just cut off the cable wherever you want and then feed it through here.
Yeah, exactly. Terminate it onto that block. And the voltage window in this is 8 to 15 volts, so pretty wide window.
Yep. Same on the well, I mentioned the power. Same on the power cable as well. We give you the flying leads, and you just connect it with the length you want. We also give you just a serial cable to connect to the unit, a USB serial adapter, which we find very, very helpful in the field. It speeds up your communication and data download rates. A thumb drive that gives you the software and the manual, and an AC power adapter if you need it. Now, Ron alluded to the pipe ring earlier. This is optional, but I think a lot of people are going to find it handy because it's designed specifically for the IQ. The holes are drilled where we expect the IQ hardware fits, and it's meant to just slide into the pipe, and then you tighten it up with the scissor mechanism here.
Yeah, you could conceivably just bring that thing in obviously less than what the diameter, the internal diameter of that pipe is, and with a electric drill, you know, with a socket on the end, you can expand that thing pretty quickly. And even still, there are still some holes in there. If you wanted to attach it, you know, if it's like a real thick PVC type of pipe, you still have that opportunity, and it might be recommended if you're going to experience real high velocities in there. But anything that we deployed already in the beta testing, we saw velocities upwards of 5 or 6 feet per second, and that thing held solid in there. So
you don't have to use a pipe ring, like Ron said. If the pipe is thick enough, make sure it's thick enough. You could actually drill into it too and just mount it to the bottom.
What's also pretty neat as well is how easy it is if you wanted to rotate that thing. If you get that in there and you realize, gee, that pipe's full all the time, you can crawl in there after the fact and just invert the thing 180 degrees and mount that instrument up at the top, or even at a 45-degree angle, and just modify the through the software. Just tell it, where its X and Y coordinates are now, and it's that simple to change the locations of it pretty quickly.
Another thing I like about the design of the pipe ring here, it's a small thing, but here you see how the cable comes up, and it's very neatly zip-tied around the pipe, just to get it out of the way and make sure it's secure, because that is a critical thing that is sometimes overlooked, just making sure your cable is secure and not just flapping around there in the flow and getting stressed over time. And once it flexes one too many times, there can be intermittent problems that just turn into a nightmare. So a lot of stupid or big and small problems just can be solved if you make your installation of the cable as well as the instrument clean. Probably don't need to go down the full list of specifications, but they're here if you want to see them. Our depth ranges for the IQ and IQ Standard and IQ Plus are going to be a little bit different. But for the pipe anyway, our range is up to 16 feet. We go up to diameters of up to 16 feet, and the velocity range, it can go up to 16 feet per second, so pretty easy to remember. So now we sort of explained about how it was developed, sort of explained what exactly it is, but here's some slides that I think will show you what we think are the key advantages and how you might find it useful in your particular application. First of all, unlike many other pipe flow measuring devices, this one works well under all conditions. The pipe can be partially full, it can be completely full, or it can be pressurized, and as you see here, that pressure is up to 42 psi.
Yeah, I think this thing has a full rate of 43 psi is what's specified in there. So traditionally in the older, say, Argonaut SW, they were able to be used in a pressurized pipe, but we really did not have any algorithms to compensate for pressurized flow,
right.
Which there's a whole different hydraulic dynamic, and much more than we want to get into here, but it is different. So the instruments did lend themselves well to full pipes that were in a gravity flow situation, where they were a full pipe in gravity. Now we have the ability to do pressurized,
right.
And there has again some of the algorithms and the modeling that's taken place to accommodate for the different conditions in pressurized pipe. So it's just another
which
dynamic.
People are starting to employ more and more.
Oh, sure. In the irrigation market, everyone knows, or some of you that are in this know, that there are the complexities of the what open channel brings to the table with evaporation and seepage and the environmental weeds and pondweed and everything. Pipes are becoming more prominent as it's a more efficient way of moving moving water between between the source and the grower out there.
So second, we have multiple beams that cover more pipe cross-section and measure more water than ever before. So as you can see, sort of just a visual to give you an idea of what the beams are actually doing when they're installed. This red line represents the forward-looking beam. Hard to see, but right behind it there's a green line that represents the backward-looking beam. So you have beams that look upstream and downstream. This third beam, beam 3, looks out to the right. Beam 4 looks out to the left. So whereas in the past, an instrument might measure here in the channel, and in the case of SonTek, it might even give you profile information at discrete points within the water column to make a well-informed mean velocity flow from which to calculate your mean velocity from which to calculate your flow. So SonTek's velocity profile was pretty rigorous to begin with compared to some other flow models that would just give you one number, just based on data coming from anywhere in here. We know exactly where these beams are. That informs how we turn that velocity into a flow calculation. But now we have more information about the flow field on both sides.
Yeah, you've got the two beams that are the skew beams now that are giving you a whole different dimension. Prior we had a vertical plane we would measure, or a horizontal plane, 2-dimension, and that was it. Everything else was assumed, and we had to do a lot of estimating. With this instrument, we're not doing so much estimating anymore. We're actually physically measuring it. As Janice pointed out, that we are measuring up and down each one of those beams, and I believe it's about every 2.4 centimeters. We're actually getting a velocity, a 2D velocity component. So if you add all 4 beams in, it gives us a 3-dimensional picture of the cross section or the section of pipe that you're measuring. Obviously, we're still not measuring the whole thing, and that instrument has never been developed yet. But this gives us the best of both worlds right now in using just a minimal amount of transducers, optimized where the at the angles of those beams and where they're located on the device.
Yeah, I think another good thing to mention, because we have this graphic up, is a good way to explain just how the instrument, how we can get potentially equally good data in a partially full pipe. The instrument knows when to cut these beams off. We have that acoustic vertical beam. We have that pressure sensor. So say the water level was only halfway. The instrument would not use information beyond what the vertical beam or the pressure sensor was telling it. So if the pipe was half full, this was totally empty, the instrument would know that, cut these beams off, and still make a well-informed flow calculation. So under more and more conditions than before, this instrument can handle those changing conditions. We're using real flow, not just theoretical, or real velocities, not as much theoretical, and just it'll handle more difficult situations when, especially in cases that don't conform to a textbook. So if you're out there and you have been having certain difficult sites, this may be something that might work. So another key advantage, which we hit on a little earlier, was this SonTek SmartPulse, or SmartPulse high definition feature that gives you the most high resolution, high accuracy data. And the way we do this, as mentioned earlier, is we use those 3 different acoustic processing techniques. And we won't dwell too much on acoustic theory, so I'll give a sigh of relief there. But those, to summarize, are pulse coherent, pulse incoherent, or narrowband, and broadband. And in the past, you would have needed a separate instrument to do each one of these processing techniques. One instrument in the past could only do pulse coherent. Another one could do incoherent, but it couldn't do pulse coherent or broadband, and so on. And each of these techniques is very good in certain situations. Pulse coherent, for example, is very good at delivering data when the water is moving slowly and it's shallow. And then there's a certain threshold at which it does really, really well, but then it doesn't anymore. Broadband and incoherent work well under their own situations. But now, using SmartPulse, we have access to all 3 of these acoustic techniques. So we don't have to deal with meeting that edge of where the technique is starting to break down. We just decide to switch to the better technique, and we still get the best data possible under changing conditions.
For some of the users that have an S5 or an M9, an example of where you can see the switching taking place is when you're making a transect, a discharge measurement, and that you'll be moving along perpendicular to flow, and as you're going along on your track, you'll notice that you might be measuring maybe up to 15 cells, and then it drops to 8 cells, and there's something changing. Maybe it's the depth, or maybe the velocity, and it's changing on the fly. Things are being done in the background. This is exactly the same as that, and just to expand on that processor again, because this engine in here is the same one that is in the M9. This one's got even a little bit more smarts because there's the modeling and the algorithms. We're not just doing an open channel flow. We're computing flow in different geometries, different cross-sectional types. So that's where a good example of where you can see pulse incoherent, pulse coherent, and broadband switching back and forth for those users that have that instrument.
Another key advantage, we can handle big pipes, but I realize that not everyone out there is a big water or irrigation district that has these big 3, 4, 5-foot pipes, or even bigger in some cases. I know there's other users in different situations that will find it useful in smaller pipes and smaller culverts based on what kind of environment they're in, what kind of environmental monitoring they're doing. So it will handle those smaller pipe diameters too. So speaking of pipe diameters, another of the big key advantages is that we can handle those small and large pipe diameters, but we can also handle irregular shapes. So we can, as you can see here, the pipe diameter can be more of an ellipse. And it doesn't even have to be a shape at all. It could be something strange, and we give you the option of plugging that channel geometry in a customized way. So it can literally handle any cross-sectional shape.
Yeah, definitely. I think this is an asset, especially in some of the, I'll go back and use on the irrigation market, where some of the delivery or pipes that you may be moving water throughout many years, decades, have changed their shape, and they're very non-symmetrical. And again, something to say is in the installation of this, which is key, is to make many different measurements to ensure that the thing is true. And if it's not, then you measure that and you can input it into the XY thing for the area, and it will accommodate it. So just like Janice said, it's very flexible now, and it will accommodate any shape or irregularity of that pipe or open channel.
So next, as we mentioned a little bit earlier, you can see it has multiple transducers that we use, but it's really all in one packaging, and all you need to do is supply the power at that end of the power and communication cable. It's not complex. Installation is just as though you were installing one transducer. So I'm thinking of other situations. For example, you have multiple transducers in a travel time system. Each of those transducers is an array and would need to be installed and checked, and have their own wires at each different place in the pipe. In contrast, the IQ gives you that kind of profile data, but you just literally pop one piece in and go. And you can have the flexibility over time to change whatever output that you want. We output serially, SDI-12 and Modbus, and all of that's software driven, so there's no need to change converters or buy different hardware if you want to move from one site to another, or your telemetry system changes, or for whatever reason. All of those communication protocols are not hardware controlled, they're software controlled, so no extra hardware needed to change those communication protocols. So like I said, that's basically, I just kind of got ahead of myself, didn't I? So all those protocols are built in, and if you need the 4 to 20 output, it comes with the flow display.
One thing I'll just expand on with the flow display, compared to the older flow displays, I mentioned earlier about the mirror codes, and the redundancy, or the checks and balances that are going on with, let's say the vertical beam and the pressure sensor, kind of checking up on each other. So this instrument with this flow display will, if there is an error or an anomaly or something, will output an error code on the display. And then you'll be able to go to a chart or a table and look that up and determine what the what the issue is with the instrument. We didn't have that capability before, but it's available now.
So just very quickly, this is kind of a busy slide, but to summarize the differences between the different IQ models. The IQ standard is the most basic model. It will allow you to measure flow in any open channel situation, an irregular or trapezoidal channel, but it will only output using SonTek's proprietary flow algorithms. If you don't do complex modeling or developing of ratings, then you might not need extra processing capability. All you might need is an IQ standard. But if you do need open channel flow with the ability to do more post-processing, to see more parameters, to actually get that velocity profiled information in your hands, you'll need an IQ Plus model for open channels. The IQ Pipe is similar to the IQ Plus in that it will let you, if you need all of that information, if you want to be able to do a rating and not just use our proprietary flow algorithms, you can do that. Now, the question often arises, can I use an IQ Plus in a pipe, or can I use an IQ Pipe in an open channel? The question is yes and no. Proprietary flow algorithms that we provide are specific to the type of instrument that you buy. So if you buy an IQ Plus, proprietary flow algorithms will be for open channels. If you want to do your own rating, or velocity indexing as it's sometimes called, for a pipe, you can do that with the IQ Plus. Similarly, if you have an IQ Pipe, the proprietary flow algorithms that we put in there are for a pipe. You can put it in an open channel, but then you're going to need to rely on your own indexing or rating to turn our velocity into that flow. Hopefully that was clear, but let us know if you have any questions about where each one should be installed. Won't get into the software too much, but it is the same for all IQ models, but what I did want to point out that a lot of our users find they like about the SonTek software and the IQ is part of is this software smart page. There's one page to the setup. Hopefully, we like to think it's not complicated, but the user essentially just starts at the top here and then goes down looking at each parameter offered, and when you get to the bottom, software has been checking on you and making sure that you've entered in all the necessary parameters, and as you go, the software turns these lights green for you. So you can make your way down, see the green, you know you're good to go, you come down here and you hit Start Data Collection. Hopefully very simple, and even while you're programming in your channel shape, you get graphical feedback as you go, so you should just be able to know, looking at it visually, if you did it right.
Yeah, I don't know if I talked about this, but one of the things, first thing up here in the system information, something I think everyone will find is useful, especially if you've had experience using the older Argonaut platform, or anybody's platform for that matter. If you look over View Live Data and Download Data, you can actually, while the system is collecting data in run mode, you can click on View Live Data while you're interfacing with the instrument, and you can look at instantaneous data of what the last measurement is sitting in the buffer in that instrument without having to stop it, download, and process it.
That's right. That's a very good point.
Second is being able to download data. Again, same thing. While the system is collecting, you can download data. So it's a real time saver that allows you to stay on site at a minimum time while viewing, getting a real accurate picture of what's happening with the instrument.
All right, now we're going to move on to some real data and real examples. So this is our first example, one that Ron did up with South San Joaquin Irrigation District. And you can notice from this picture that they used the pipe ring, and they installed it on top of the pipe looking down. And of course, the assumption that we make in this situation is that the pipe will always be full. Another thing you'll notice, what I like about this picture, is that you can see they took their measuring tape out, and they're measuring the pipe diameter here.
Yeah, again, most of the time you can look at something and get an idea that if it says 36 inches, you can kind of eye it up, and hopefully it'll look symmetrical. But it's always best, and we found, because this always wasn't the case, is to take a measurement, in the vertical and the horizontal, and sometimes even at a 45, and then average them, because really most of them are not true. There are some differences in the in the diameters, based on most likely the culprit is the installation of the pipe when it was done many, many years ago. So this instrument is very, very accurate, and it's measuring in a precision down to centimeters. So if you are not meticulous in putting in the information for that cross-sectional area, that is going to be apparent in your flow computation after it's measured the velocity. So what needs to be done is just be very meticulous and ensuring that that cross-sectional area is as accurate as possible. That's right.
The IQ is that much more, the resolution is just that much better than has ever been seen before by SonTek or other instruments, that you will start to notice what seems like a really insignificant thing. You will be able to see it. And it's not necessarily that it's creating errors in your data. You can just see now where there was an unknown that was never accounted for. So again, this is sort of just a real world application of showing you how this instrument was set up in the field. We went down, entered some basic information. We set up our sample duration, which was 120 seconds, which means the instrument will wake up, average for 120 seconds, and it will do that on an interval of 300 seconds. So it'll give you a 2-minute average every 5 minutes. Again, you can look at this graphical display and make sure you set it up correctly. You can check or you can choose your theoretical, or if you have a rating, enter your rating in this section. Select the output units you want, whether you want English or metric. And in this case, they were using the analog output, so we can see what parameters they chose to output. And this is what the data looked like. You can see the pipe was full to begin with. There wasn't any flow at the outset. There wasn't any volume being recorded. They turned on the pumps. Right away, that flow jumped up. And as soon as that flow jumped up, this graph over here is the total volume. The flow jumped up, and then the instrument started recording that total volume. So you see that nice increasing line of total volume, and the flow is constant. And the flow here is around 13 point something feet per second. So our next data example is actually along the same line, if I'm not mistaken, at South Central Keene Irrigation District, but we took an IQ, and instead of putting it on top, we put it on the bottom. We did our setup pretty much the exact same way. And this is what that data looked like. Similar depth, similar flow. They turned on the pumps. Total volume started to be recorded. And where's our flow here? Flow 13 point something. So I think I'm presenting this to show I think SonTek has done their homework. It doesn't matter whether the instrument is top looking down, bottom looking up. Under the same flow conditions, we give you the flow number.
Definitely validates itself, especially when they were mounted just about 100 feet apart from each other.
So here's a second up-looking example, and here's a picture of what that looks like. This installation is a little bit different, and it had its quirks, didn't it, Ron?
Yeah, a little bit. You can see, obviously I shouldn't say that. It's partially full. You can see the scour. There it is. Okay, so you can see the scour line here. This pipe is decades old, so there is a lot of material. The clay was hard clay, packed sand. Something like this, unless you went in there and cleaned it, I would not envision using a pipe ring in here, just because I'd be afraid it wouldn't hold. There's the sand and hard packed clay was about 1 inch thick. You could see a lot of it had to be cleaned out to put this thing in here. So again, talking about being meticulous and ensuring what your real cross-sectional area is by making measurements this way, and this way.
Right.
And
then it's it might be a little bit hard to see if you haven't seen our riser mount before, but what Ron used there was the option. It is an accessory that can come with the IQ if you want it, is this riser mount that lifts it about an inch off the bottom and allows flow underneath.
Right. That was really designed for putting it in cross sections or open channels where you may have had you know, a sediment transport or you know, moving bed material, debris. But in the situations like this, we found another good reason to use the thing, because it will, if there's this hard packed you know, debris inside the pipe, you can just chisel it out and bring the thing up and bring it up above all of that silt and everything.
And looking at the data real quickly, this is a very specific installation site with a very specific set of circumstances. And I don't know if we have time to fully explain what was going on here, but you will notice the data came in all at once. So the velocities you'll see weren't being registered at the beginning of this time series, but they shot up really fast. And it's just the way, it just had to do with the way this pipe situation was set up. But the velocity shot up. I didn't graph velocity for you last time, but this is showing the velocity. This is more information than probably you've seen before, but we have 4 lines showing you velocity and similar to before. Once it got full, depth remained constant. Flow, you know, started increasing a little bit actually, and then total volume being recorded all the while.
Well, I can tell you, I mean, we deployed it at 8 o'clock at night, so went back to San Diego, and the deliveries were then being, so we started it at that night, at 8 o'clock that night, but the delivery wasn't being made. The ditch tender, Zanjero, turned the water on. You can see he opened up the gate here probably about 6:45 approximately, and that's and it's so what this shows is that this thing can be left in an autonomous mode and out there and
no water,
and all of a sudden water's on and water's off, and that was the way this thing was designed and built to be used.
So lastly, just thought you might find interesting some of our some pictures that Ron has from the field. I like this one on top. It was in a pipe, and we can see how they created this access panel, put the IQ in there, and that's what the pipe looks like on the outside.
Yeah, and this was something that we just wanted to try and a little collect some data and doing some of the data testing. We Janice has alluded to that minimum diameter of 1.5 feet, 18-inch pipes. This was a 10-inch pipe, and we had access to it. So we threw it in and collected data from it for about a week, and it worked. So I think in the future we're going to try and collect a little bit more empirical data in these smaller pipe diameters, and you know, I'm going to try and plead a case because I think that this device will work in smaller diameter pipes. You know, especially when we're starting to measure, you know, our first cells. We can get 2 cells of data in 3 inches of water.
Yeah.
So it'll work.
And yeah, what about this bottom one, Ron?
Okay, so that
one that's actually kind of a fully integrated with a
yes,
solar panel. So
it just shows we built a couple of just a little temporary stations that we were moving around from site to site, and all it was a solar charger in the back. Can't see that, but there's our flow display and a 10-watt solar panel. Again, using the new processors and current components on the market, these things are very, very low power now. You know, we're talking half a watt when they're measuring. Even the flow display, if you don't have analog outputs, I think is only about 250 milliwatts. So, and that's when they are actually active. And then when they go into a sleep mode, it's milliwatts. So 5-10 watt solar panel is all you need on these things now, and that'll suffice, and they'll be good for many years out there in the field.
And this is our last example, and it's pretty revealing. Ron can talk more about this installation. In this particular, in the picture on the left, you can see where the IQ pipe was installed in that pipe, and in this picture, the water line is clearly not full, but you can the water is clearly, or the pipe clearly is not full. But as Ron will point out with the pointer there, it was, when this data was collected, the water line was up to that mark, and the pipe was completely submerged on the outside.
Yeah, this is one of the first ones that we did in testing of the IQ in the pipes, and testing these algorithms. And one of the things we wanted to find out from the grower is if he knew of a full pipe, and they pointed me to this one. And you can see from the scour up here, it should be full. And it was when we looked at it the first time. What we perceived to be full when the water was exiting the pipe here. So deployed the instrument, installed it, and started, I think it was a 24 or 36-hour run.
What did they expect? They expected it to be full, and they expected a certain... Right,
and it was, I think, around probably a 12 or 14 CFS.
What was the diameter?
A 30-inch.
It was supposed to be it is a 30-inch
yes.
pipe, yeah.
So what was interesting about this is when the run began, we saw our data shot up, and that's what we expected. But interesting enough is, look at the depth. The depth was only about, 0.75 of a foot, 8 inches. Okay, here's our depth down here. Okay, and the velocity is up there screaming almost at 10 foot per second. So there was considerable slope in this, and the reason why it looked like it was a full pipe was because as soon as it exits here, it shoots off this way 90 degrees. So the turbulence and the backwater effect from it hitting that wall in here, everybody thought, hey, you got a full pipe here. But really, internally, where the instrument was, and we put it in only about 8 foot up in there, there was only 8 inches of water above it, but it was ripping at about, let's see, about 10 foot per second, just a little less than 10 foot per second on the downstream beam. So what, again, the cool thing about this instrument is it is going to tell you a lot of information that you did not know, and it just because of the way that we can monitor it even in real time without having to stop it. It's a great platform to use.
And that was our last example. So I realize we're kind of getting close to our ending time. And we thank you for joining us. We're probably going to go over, but we'll just take some time and answer a few of the questions that came in. And for those of you who asked questions, and we certainly don't have time to answer them all, but we will answer them after the webinar is over and registered. A copy of all of the questions that were asked and all of the answers that we provide. So let's see, what is our first question?
This one I want to add. That's interesting.
Is the pressure sensor sensitive to dry, mud, or dry and mud water? Does the pressure value change between clean water and mud? Well, I have to say the instrument wasn't designed to handle mud. It probably wouldn't give you much of an acoustic signal if it's truly mud that it's operating in. What I will say about, and Ron can jump in if you want.
One of the things, we talked a little bit about the pressure sensor, but one of the things that is new compared to the way we calibrated the pressure sensor before was that we had to bring it out of the water, zero it out, put it back in, and deploy the instrument. You can now calibrate the pressure sensor in the water.
Mm-hmm.
So that is one real quick aspect, because there have been many times when you're ready to deploy and leave a site, and it's one of those Homer Simpson moments where, oh, I forgot to zero out the pressure transducer. Now you don't have to worry about that.
That is true.
You can do that with this thing. Does the pressure value change between clean water and mud? Well, again, that's sort of subjective, because this thing really wasn't designed for mud, and I wouldn't use this thing in mud or a very high concentration of
I guess
particles.
Mud is a subjective term, but what I will say that it does. The pressure sensor is more resilient to higher sediment water than any of our other instruments, and there's a couple different reasons for that. If we were to take a look at the picture of the pressure sensor again, it's not just a port. Oh, that's a good picture, right? It's right there. Okay.
There it is,
yeah.
right there.
Okay, so what we've got here in this picture is the temperature sensor right here. And in the past, and with other instruments perhaps, you'd have a pressure port. I guess I used that term earlier. It's not exactly accurate. It's not just a port sitting here on top of the instrument. It's a flow-through cell. So the pressure sensor is in this flow-through cell. So this orifice is open to the water here, and this orifice is open to the water here. So the water actually flows side to side through this cell. So first of all, these orifices are not on top. So it minimizes the chance that sediment will just settle in there and then clog in there over time. And perhaps the person who wrote this question was well informed that if you do have sedimentation in there, sometimes it's not really a problem at all, but it becomes a problem after the instrument goes dry. And then that sediment hardens and packs in the pressure sensor, and that does create a problem. So placement of these orifices is different. And it's not just a port, it's this flow-through cell that would hopefully minimize and does minimize the amount of sedimentation that happens. And even the sides of the housing are aerodynamic, so the flow should shear off here and minimize any settling into those orifices.
One question here, how do you secure the IQ on gravel, sand, or cobble bed? Well, there's probably many different ways. Creatively, many different ways you could do that.
We've seen it done.
Yeah, I know we did too up near Bishop, and it was on a cobble in a natural river, and used about a 2-foot by 2-foot concrete up, so it'll be negatively buoyant, and negatively buoyant, and keep that thing down in the bed. And then attach your conduit to that and bring the cable out. And it's also going to be dependent on what you use to secure it in there and the velocities that you expect to see. I mean, if you're talking about a 1/2 foot per second, you don't have to get too crazy. But if you expect, event-like conditions where you're upwards above 5, 6, 7 foot per second, you're going to have to use something a lot more robust to make sure that thing doesn't move in place while it's secure.
And just conceptually, for example, you could come up. We often have these weighted mounting plates that we use and take when we're testing out different sites. They're very heavy. You can sink it down. The plate can be weighted, but you can also attach, say, as though it were like, you can almost picture it as table legs. You can attach a pipe or some sort of rod to the plate and then pound the 4 corners of the weight through these rods into the ground, into the river at the location that you want, and you make those long enough that you'd be confident it wasn't going anywhere. Okay, next question. Can the IQ Plus recognize an ice deck or the cross-section handle or the culvert and not an open channel? So we're talking about a situation here where it starts out as an open channel, so you put an open channel instrument in there, but then when the ice, say it's wintertime, it ices over, you effectively have more of a culvert situation. The short answer is no, we don't have an ice setting yet The instrument certainly will still operate. Probably what's going to happen, or what could happen, I guess, is that the water level will still detect the water level and continue to perform its calculations. And of course, if the IQ itself hasn't iced over, it'll still be operational in water. It goes down to freezing. It'll still give you that data.
But theoretically, when the vertical beam would detect the bottom of that ice layer, and
sure,
yeah,
it would do that. But if the water level dropped below the ice level, that's where the problems would come in. You're
sure.
right. Yeah,
yeah,
you're right.
okay.
Right. If the water were still flowing up against the ice surface, the vertical beam would still work. But
Okay.
but yeah, I wouldn't switch on the fly to a culvert situation. So good question.
Yeah, because the older SW, we had some ice. Had some ice algorithms in there that Craig had put in at one time. Let's see, what is that?
How about this one? Is the data assigned to the start or the end time of the measurement interval? The question is either one you want. You need to either time it to start at like the top of the hour or time the sample to be spit out at the top of the hour, and then just tell it how long you want it to average, and the instrument knows how to do that. All right, thanks for all the questions you submitted. Like I said, Ron and I will compile the answers for you since we don't have time to cover them all, and if you're sitting here and you registered, of course, you'll be getting that from us shortly. So thanks again for joining us, and let us know if you have any questions. Have a good day, everybody.
Thank you, everybody.